Hi all, welcome back. Now I called this video three-dimensional motion, but this should really be vector functions associated with physics. Now all of physics is pretty much modeled by a vector function. If I have a point particle, which is what we deal with, my physics teacher always tells me assumptions we make when dealing with mechanics is that all points, everything we talk about is just a point mass. That's obviously not the case when we get into inertia and stuff like that, which we'll talk about later in this course. It rotates and it's not just a point mass, but when we're interested in its motion from a macroscopic point of view, we can treat it as a point mass. But anyways, we have our point mass, and we also define a coordinate system. There's our coordinate system. That was actually a decent set of orthonormal basis that I drew. I'm usually pretty bad at that. And we can add a third dimension if we so choose, but why not 2 dimensions to keep things simple? We can define the motion of our particle by some position vector. Now, my position vector, I will call this r. Now, that defines where my position is, but my position might be different at other points in time. So as I go through time, my particle might move through space like that, or something like that. And because of that, we have some sort of velocity. And our velocity is called v, and that changes through time. So both of these change through time. Our position and our velocity all change through time, and they are vector functions. These are vector functions of t. So we have nice applications for vector functions. Then we can break it up. We can get a vector function for, or we can get a parametric equation for x of t. We can get a parametric equation for y of t. Then we can get a parametric equation for x of t for our velocity vx of t. Then we can also get vy of t. There are infinite possibilities, or not infinite, there are many possibilities that we can talk about. Anyways, let's keep talking about three-dimensional motion. So we have vector functions in physics. We can define, if I have my velocity vector function, I can define that as the derivative of my position vector function. Now this should all make sense. Additionally, if I want to have the speed, if I want to determine the speed, well, the speed is the rate at which the arc length is being consumed, if you will, or being transversed. So the velocity, the magnitude of the velocity is equal to the speed. So if I want to find, if I've got parametric equations, x of t and y of t, for that describe my motion, then if I want to find the speed, then the speed is equal to the square root of x squared of t derivative plus y squared of t derivative, because that is equal to the magnitude of the velocity function of time. And we can rewrite this as the magnitude of r dot of t. And then finally, we can define the acceleration function. The acceleration vector function is equal to the first derivative, v dot of t, which is also equal to r double dot of t, or r umlaut of t, as I like to say, because of the German connection you have there, which is kind of fun. Anyways, that's enough of me talking. Why don't we do some examples? Here's one example. Let's say that a particle starts at 1, 0, 0. So let's define a coordinate system. So I've got my x-axis, my y-axis, and my z-axis. Our starting point is 1, 0, 0. So we go 1 point over on the x-axis. And that's my starting point. So our position vector at the beginning looks like that. That is r naught. And then we also have an initial velocity of 1, negative 1, 1. So we have a derivative instantaneously at the beginning of 1, negative 1, 1. And our acceleration, we have an acceleration function which is equal to 4t, 6t, and 1. Now I want us to find the velocity and the position functions. Now what we learned in single variable is that if I have acceleration, or well, if I have acceleration is equal to the first derivative velocity is equal to the second derivative position. Likewise, the position is equal to the first integral of velocity, which is equal to the second integral of position, or of acceleration, sorry. So anyways, we know that with vector functions, if I take an integral of f of t dt, I get f of t plus c. So our constants of integration were actually given right here because those are our initial ideas that we've got. So we've got the velocity is equal to v naught, our initial velocity, which is our constant of integration, plus the integral of acceleration with respect to time. Now, if I want to take the integral of acceleration, I take this, and then I take the integral of each component. That's pretty easy. So I get my initial velocity, 1, negative 1, 1, plus the integral of acceleration, which is 2t squared, 3t squared, and t. So I can just apply addition principles, and I get 1 plus t squared, negative 1 plus 3t squared, 1 plus t. Now if I want to find position, then I do the same thing. I take the initial position plus the integral of velocity, which is 1, 0, 0, plus t plus 2/3 t cubed, I'm integrating, then minus t cubed plus t cubed, and then t plus 1/2 t squared. I apply addition properties, I get 1 plus t plus 2/3 t cubed, negative t plus t cubed, t plus 1/2 t squared. And that is my position function. Let's do another example. Let's say that an object with mass m moves in a circle with angular speed omega and an initial position, or a vector function describing position modeled by r. Find the force of the object to the origin. So let me draw this out. So you've got a circle, and I know I said 3 dimensions. This is 2 dimensions technically, but you could always make this a polar problem, which would make things interesting, but do whatever you want. Anyways, we've got omega as our rotational velocity, and r of t is a vector going from the origin to a point that moves around the circle. So r of t is equal to a cosine omega t and then a sine omega t. This is very common in physics that you see this. So now what we do is we differentiate to find the acceleration, because we got to use Newton's second law. Newton's second law says that the force, which is now a vector function, is equal to the mass times the acceleration, which is also a vector function. So we want to find acceleration because then we can find force. Anyways, so v of t is going to be equal to negative a omega sine omega t and a omega cosine omega t. We can do that easily with the trig derivatives in the chain rule, right? Because we got to take the derivative of t. Now, if I want to find the acceleration, then I take the derivative of the velocity, and we get negative a omega squared cosine omega t and negative a omega squared sine omega t. Now what we can do is we can plug this into Newton's second law, which says F equals ma. So now we have F is equal to negative m omega squared. We can pull the omega squared out. A cosine omega t, a sine omega t. And why did I leave the a in there? Well, I left the a in there because now we see a direct correlation between this and this. So we can rewrite this as negative m omega squared r of t, because that's a really nice property of the trigonometric function, such that if I take, it solves this differential equation. If I say d squared f dt squared is equal to f, that is solved by cosine, and sine, because the other alternative is that d squared f dt, or df dt is equal to negative f. That is, df squared dt squared is equal to negative f. That's the differential equation that we want to use. That's just false. Sorry about that. In the next video, we are going to keep talking about physics. We're going to talk about Kepler's laws. And then after that, we are done with vector functions, a great introduction. And then we are done with our 3 prerequisite units for multivariable. And then we are going to dive into multivariable functions and, most excitingly, partial derivatives. I'm getting so excited for it. All right, we'll see you in the next video. Thanks for watching. All right, next time, Kepler's laws. See you then.